Okay, in this second video, I want to talk about some of the other interpretations and assumptions necessary for linear regression. First, we need to check how well our linear model actually fits the data. The value r is the correlation between the two variables. However, if we use r squared, also called the coefficient of determination, then we can find the percentage of variance of y actually explained by x. Ideally, we want an r squared as close to 1. The standard error of the regression measures the magnitude of the regression residual and is not associated with the standard error from descriptive statistics that you might have learned in a previous class. When we calculate out the r squared, what we are looking for is the amount of variance actually explained by our variables. We look at the sample variance of our dependent variable y divided by the total sum of squares, which is the part explained by our model plus the residuals, or what was not explained by our model. The r squared value will always be between 0 and 1, where 0 means no variability was explained, and 1 means all the variability was explained. Now, if we go to the regression we ran the other day, we can see that our r square value is right here, and it's 0.89, which is pretty close to 1. So we can explain a lot of variability in our selling price by using the square footage variable. Our standard error is here. Standard error of the residuals. This next thing we want to check is something called the f value and the probability of f, or the p-value associated with that f statistic. We use the f value to calculate out our p-value. This p-value, if significant, tells us that our model is statistically significant and that we can continue analyzing the coefficients. So hopefully you learned about ANOVA in previous classes, but the ANOVA and regression are important to each other, but let's see. Right here is the F statistic, which the only reason that's important is for calculating out our p-value here. And we want our p-value to be less than 0.05, and we can see that it's 0.0001, so it's a very statistically significant model. So when we look at that, then we can go down and start looking at the coefficients and interpreting them. In order to claim that one variable causes another variable, we need to check a few assumptions. There are 3 necessary assumptions for causal inference. The first is that the conditional distribution of the population has a mean of 0. If it doesn't have a mean of 0, there's something we can do called centering the data, which basically you subtract the mean from all the data points, and then it should center it around 0. The second is that our data is independent, identically distributed random variables. That's what the IID is. Which basically just means the data came from the same distribution, same data, and was independently selected by a random sample. That's why random sampling is important when you're looking to do inference. Finally, there are no large outliers that might skew our regression. Thus, we would need to remove outliers before we ran our analysis. Now, in general, there's a set of assumptions. Some of these are going to be more important when we get to multiple regression, but we'll talk about them as we go. So there are six if you count the last assumption, that must hold in order to perform regression analysis. There must be a linear relationship between the variables. It must be normally distributed, no multicollinearity, no autocorrelation. It must be homoscedastic and meet the sampling size condition. First, there must be a linear relationship between our dependent variable y and our independent variable x or x's. Also, we need to check that there are no outliers here. This is best tested with a scatter plot. And that's pretty easy to do with Excel. Insert scatter plot. And it looks like our data is relatively linear. If it had a U-shaped, then it might be quadratic, or if it had other shapes, but this data looks relatively linear, which is good. So our first assumption is met. The second assumption is that the samples are drawn from a normal distribution. This is best checked with a QQ plot or normal probability plot. If we go back to what we talked about before with the law of large numbers and central limit theorem, this is why those are important, because in order for us to run this regression, it has to be drawn from a normal distribution, and we know that as the number of samples increases, the law of large numbers and central limit theorem, it's going to approach the normal distribution. That's how that kind of all correlates back together. Sometimes we may have to transform our data before we can run our analysis if the QQ plot doesn't come out right. So I'm going to rerun this and add in those other. We're going to rerun the regression, and this time we're going to look at the residuals and normability plot. So let's output this to a different page, new worksheet. Yeah. So this is our normal probability plot, and the same thing. We want this to kind of be very linear, and that means that it comes from a normal distribution. So our second assumption is met using the normal probability plot. The third assumption is little or no multicollinearity. It has to do with the correlation between independent variables or X variables, but we will talk more about this with multiple regression because right now we are focusing on only one X variable. So you'll have to wait till multiple regression to learn more about this. No autocorrelation. This is something we're going to talk a little bit more about later also. It's another special topic that we can come back later to in the semester. Homoscedasticity means that all the residuals have equal error. What is not good is something called heteroscedasticity, which is what the image is and shows that the error changes or is not consistent. So what we want to see is that these data points are consistent both above and below our line. So if we look at our residuals, what we want to see is that our data points are both above and below the line in equal amounts and equal distance from the line. So I mean, this is pretty close to a good residuals plot, but And the last general rule of thumb is you should have at least 20 samples for each independent variable. We have one independent variable, so we would really hope to have 20 samples, but we only have 9. So that last assumption is not met. So we should really go collect 11 more samples just to run analysis on this one variable. When we get to multiple regression, we'll have 3 variables, so then we would want at least 60 samples so that we can get a good regression analysis. But hopefully that helps you understand the assumptions necessary to run linear regression and a little bit more about interpreting the results that we get from Excel.